Oh yeah, here we go. Here we go. This is help video, our sixth one over our 8-20 test premiere, which is essentially our review for Unit 8. This is our sixth video over this 25 objective question packet. And we will pick up with question number 20. Question number 20. Use the solubility table below to determine which one of the following double displacement reactions would not take place. Let's start off taking a look at letter A here. Letter A, we have barium chloride aqueous reacting with sodium sulfate aqueous. Aqueous means these ions are pulled apart. How do we know barium chloride is in fact soluble? Well, here's chloride right here on this list. We go down to barium. There's an S there. On this chart, S stands for soluble. On this chart, I stands for insoluble. So yes, barium chloride would be able to be pulled apart. What about sodium sulfate? SO4 is the sulfate ion. We learned our polys. Where is the sulfate ion? It's on this chart. We go down to where we find sodium, which is right here. We look across. There's sodium. There's sulfate. It is soluble, so that salt would get pulled apart. So when we mix these solutions together, we have barium ions floating around with chloride ions, which are now floating around with sodium ions and now floating around with sulfate ions. The sodium ions can bump into the chloride ions. If they do, would they form a solid that water could not keep pulled apart? In other words, would they form a solid precipitate? Let's find sodium. Again, here's the chlorides. We go down to sodium. And if you remember some of those rules that we learned, we come down to chlorine, down to sodium. That is, in fact, soluble. That is going to be soluble. So that would stay in aqueous solution. What about the barium sulfate? Let's go back and find the sulfates. Here's the sulfates. We go down to barium, sulfate. That's insoluble. When the bariums bump into the sulfates, water couldn't pull them back apart. The Ba2 pluses will be pulled together with the 2 minuses, strong positive 2 charges. They would cling onto each other and not be able to be pulled apart. This reaction would happen as it's shown. Letter B, what about sodium phosphates? Is sodium phosphate aqueous as it's shown there? Well, we'd have to find the phosphates. There's the phosphates. We know sodium is all the way down here at the bottom. There's the sodium. Sodium phosphate is soluble, as they showed here. What about copper 2 sulfate? That's the one that makes a blue solution. It is soluble. Here's copper 2. Here's the phosphates. Copper 2 phosphate. Whoops. Copper 2 sulfate's what we're looking for. Copper 2 sulfate. Here's our sulfate. Here's the copper 2, soluble. So we pour these two together. They're going to be bumping into each other in solution. The sodiums will bump into the sulfates. What will happen? This is saying nothing. They'll stay floating around when they bump into each other. Water can keep them pulled apart. Sulfates, we come down to sodium. Yep, soluble. They would stay apart. This is saying when the coppers bump into the phosphates that they would join up and not be able to pull apart. The copper 2s would not be able to be pulled apart from the phosphates. We already accidentally looked at that column a few seconds ago. There's our phosphates. There's our copper 2s. We come up over insoluble. They would precipitate out of solution. Letter B is correct. Letter C, sodium carbonate. Is it soluble? We come down to the chart. Sodium carbonate is claimed to be soluble. Here's the carbonates. A lot of the carbonates are insoluble. We come down the list. What about we're looking for sodium carbonate. We come down to the list. Here's the sodiums right here. Here's the carbonates right there. They are soluble. So water would be able to pull those apart. What about lead 2 nitrates? Here's our nitrate column right there. If we look on this list, here's our lead 2s, there's our nitrates, they are soluble. But what happens when we pour these two solutions together? The leads would start bumping into the carbonates, the sodiums would start bumping into the nitrates. Sodium nitrate, they're saying, can be pulled apart by water. They would not precipitate out of solution. We know that most nitrates, we know that most alkali metals and so forth. Here's the sodium. If we look across that sodium column, sodium with anything is soluble is one of our general rules. So yes, that will stay pulled apart. What about the lead 2 carbonates? A lot of the carbonates are not soluble. We look at those insolubles. Here's the carbonates. A lot of them are insoluble. Lead 2 carbonate is one of the ones that's insoluble. That would precipitate out of solution as they've shown here. What about letter D? We have hydrochloric acid, one of our 6 strongest acids, reacting with potassium hydroxide, one of our strongest bases we can have in solution. What's going to happen here? Well, this is a double displacement reaction. This hydrogen's going to dissociate off the chloride, join up with the hydroxide ions to form water. This is double displacement, specifically acid-base neutralization reaction. The potassiums will end up with the chlorides. Water's our product, which is one of the 3 driving forces. Solid precipitant is one of the driving forces. Water's the second driving force, and the formation of a gas is the third driving force. Is the potassium chloride in fact soluble? If you look across the potassium column, it is soluble with just about everything. So yes, that potassium hydroxide would be soluble, and potassium chloride would also be soluble. What is wrong with letter E? This looks like they're trying to write a double displacement, where the first thing here is joining with the second thing there. Sodium nitrate, we already know sodium in anything is soluble. Look down that list. Potassium with anything is soluble. Look down that list. Here, they're showing potassium chloride forming a solid precipitate and precipitating from solution. That's not going to happen. It would stay aqueous. When both of the products are aqueous, there's no reaction. They're floating around here, they're floating around here. Nothing changed. Letter E would not happen as it's shown. We go to question number 21, and that's what they're trying to show you right up here. NaNO3, follow that arrow down, soluble. KCl should have an aqueous after it. Follow that arrow down. KCl, highly soluble. No precipitate's going to form. We come down to the next question, number 21. Use the chart above to complete the chemical equation. We have magnesium chloride. They gave us that. What about silver nitrate? What's going to happen when this reaction occurs? First of all, is magnesium chloride soluble? Here's our magnesium. Here's our chloride. That's soluble. That'll work. What about the silver nitrates? If you look down that nitrate, a lot of these nitrates are soluble, as we've learned. Look at that. S down the list. S down the list. The only one is bismuth. So we look down there. That one, silver nitrate. There's the silver. There's the nitrate. That's going to be soluble. So when we put these two substances together, the silver ions are going to float around and they're going to bump into the chloride ions. What happens when the silver ions bump into the chloride ions? Follow the arrow up. When the silver bumps into the chloride ions, that's the chloride ion column right there. We look down the list. That's that box right here. It is insoluble. The silver chlorides will precipitate out of solution. What happens when the magnesiums bump into the nitrates? The answer is nothing. Follow that arrow up. Magnesium, we already saw the nitrate column is highly soluble. That'll stay floating around. So the silver chlorides will precipitate out of solution. we have a 1 plus here and a 1 minus here. Silver's always 1 plus, chloride's 1 minus, crisscross. Magnesium's 2 plus, the nitrates are 1 minus, crisscross. We had MgNO3 2 times. So I have 2 nitrates there. I would need 2 nitrates here, so I put a 2 in front. I have 2 chlorides there, and I now have 2 silvers there, so I need a 2 in front to complete that reaction. The correct reaction is this one right here, as we've drawn up on top in that double displacement reaction. Now they want us to write the net ionic equation. For number 22, they want us to write the net ionic equation. To do that, it's easiest to write the ionic equation first. So ionic, we just take the MgCl2 aqueous. Aqueous means water pulls it apart, so we pull it apart. Mg is always 2 plus. I have 2, do you see the 2 there? I have 2 chloride ions floating around. That 2 just means in solution for every one of these, I have 2 of those. So I have 2 chlorides floating around. What does aqueous mean here? That water pulls it apart. Nitrates are always 1 minus. It's one of the polys. I have 2 nitrate ions. I have 2 nitrate ions. I have a 2 in front. Silver's always 1 plus, so I have 2 silver 1 pluses. So that's my reactant side with everything pulled apart. On the product side, I don't pull these apart because water can't pull them apart. It's soluble. So I just take that 2AgCl and write it right there for my ionic equation. Ionic equation just means you're pulling them apart. This is soluble as we learned, so we pull these apart. I would have 1 Mg2 plus floating apart, and I would have 2, if you see the 2 right there, I would have 2 NO3 minuses floating around. That's my ionic equation. The net ionic equation wants us to write which ones are changing. Which ones are changing here? Well, right here I have Mg2 plus on the left side, reactant side, and it is on the right side as Mg2 plus. It did not change. So that is not part of my net ionic. The net ionic just wants the things that changed. Here I have 2 Ag pluses floating around. On this side, I have no Ag pluses floating around. They precipitated out of solution. So that one did change. So I would write the 2 Ag plus. What did it change into? 2 AgCls. Here I have 2 Cl minuses floating around. On the product side, they're not floating around anymore. So this one did change from Cl minuses floating around to forming a solid precipitant. What happened to the NO3s? I have 2 NO3 minuses. On this side, I have 2 NO3 minuses. Nothing happened to them, so I don't write those either. The blue ones did not change, so I do not write those. My net ionic equation is the ones that did change. Letter A. The ones that didn't change are called spectator ions. The Mg2 plus didn't change. The 2 NO3 minuses did not change. Mg2 plus, 2 NO3 minuses, letter AD, those are the ones that did not change. That takes us to the end of help video, whatever number this is, help video 6, I think it is. I lost count of which number it is. As always, if you have any questions or want any of this discussed further, just email me the number. We can set up a meet. We can set up whatever you need. We can email back and forth, do another help video, whatever it takes. Please ask. Thanks for watching.